I'm very happy to be here and excited to tell you a little bit about the future. One of my friends says, whenever I talk to you, I feel like I stepped in an elevator, punched the button that says 20 years in the future, and then went go. So hopefully we'll have a little bit of a flavor of that. DARPA shares a very interesting formation story, and it's the same formation story as NASA. Sputnik was, of course, a huge existential moment in the United States. NASA was formed as a result of Sputnik, and so was DARPA. And the mission of DARPA is to prevent and create strategic surprise. And the focus is on national security. So we believe that the best way to prevent strategic surprise is actually to create a new future. So to do sustained investments in specific technical areas to create a new technology vector and a new future. It puts us in a really good position. We have the opportunity to work on technologies that we think will have the biggest impact without reference to a specific mission or set of requirements. We basically look across what we see as the biggest problems, and then we make a sustained investment in technology to attempt to solve them. So what am I doing here talking to a group of people about commercial spaceflight? Well, there's been a long history of DARPA doing commercial transitions. When you look at our, for example, our Microsystems Technology Office that works mostly on MEMS and nanotechnology, almost everything in your cell phone was originally developed through a DARPA program, and all of those transitions were directly to commercial, because that's the way that we thought the US government could make the best use, is to have this technology proliferate throughout commercial industry. We're beginning to see the same thing happen both in our software office, the Information Innovation Office, and in our Biological Technology Office. But I will tell you the Tactical Technology Office has not done a lot of commercial transitions. So we are the platform office. So we're the office that takes the component technologies that have been developed by other offices in other areas and actually integrate them onto a platform. So we're really like the advanced engineering division of DARPA. So what we have discovered is that the best way for transitioning some of these technologies for the benefit of the US government is actually through a commercial transition. So this is quite a big change in direction for TTO, and I think you'll see that weaving through. I'm just going to talk about our space portfolio today, but we're seeing it across the air, maritime, and ground systems as well. So what are the big problems that we see today in space, and how can we make a difference? So the areas of concern that we have fall into three basic areas. Of course, flexibility for launch is a big one. Right now we have a wonderful couple of places to launch from, two places that we routinely launch to GEO. On the other hand, we are a hurricane and an earthquake away from losing that capability. So we really see these long production line times. If you have a payload, you get into the queue 2 years before launch. Everything that we do in the launch area has been focused in the past on mission assurance, which is great, but it becomes handcrafted and artisanal. It's more like hand building a Maserati than a production line. The costs of satellites have gone up, and that's clearly linked to the cost of launch and the flexibility. If it costs so much and it takes so long, it darn well better work when it gets up there. And so what we see is this spiral evolution where now our space systems are also costing more and more. And finally, the area of space domain awareness. As many countries have gotten into the space domain, we're up over 63 now that have satellites in space. Now you see the CubeSat and SmallSat revolution that's going on. There are more and more objects in space. And frankly, JSPOC is having trouble tracking all of them. If any of you have launched some CubeSats in space, you know how hard it is when 27 of these things go shooting off as a secondary payload. It can take days before you can figure out which one is which. Our systems are being stressed, and they're really not meant for real time. They have been designed, the systems at JSPOC and other tracking systems have been designed basically for a very small number of government-owned satellites and looking for predictive conjunction avoidance. And so that's what it's been about. But as we grow the number of objects in space, and some of them are too small to characterize, what are we going to do about that? We're going to have a problem. So our solutions are aimed in these general areas: flexible, affordable access to space, changing the paradigm of satellite operations. And we're really looking at new architectures and at servicing. And I'll talk a little bit about each of these programs. And really trying to invest in technologies that give us real-time space domain awareness, just the same way we do in the air domain. So our access to space, we have several small seedling programs, but our two large programs in this area right now are the Experimental Spaceplane 1, or XS1 program. If you were here last year, you got an update on that from our program manager, Jess Sponable. And we are just past PDR in that program. And so you know what's happening now. That's when the sausage is being made as we move forward. We have 3 performers in this area. Boeing is the lead for one. Northrop Grumman partnered with Virgin Galactic for a second, and Maston Systems out of Aerospace Systems out of Mojave. Each are working on developing a reusable first stage that is capable of launching 10 times in 10 days, and when paired with a very low-cost upper stage, can reduce the cost of launching payloads in the 3,000-pound class to about $5 million a pop. When you compare that to what the Minotaur can accomplish and others in that class, that's just about an order of magnitude improvement. We are focused on the first stage at this point, but we're keeping a close eye on some of the low-cost potential upper stages that are being developed. The Airborne Launch Assist Space Access Program is focused on a much smaller payload class. The capability goal of ELASA is to launch 100 pounds to low Earth orbit for $1 million, including range cost, on a 24-hour call-up. And the technical solution for that was to have a small second stage that is attached to an unmodified F-15 as the first stage, and achieve that capability. And that program is also between PDR and CDR right now as well. Okay, I'd like to talk about a couple of programs in the area of satellite architectures and systems. So we have a large program called Phoenix, and we recently broke that up, I guess about a year ago, into 3 component technologies. And I'm going to talk about each of those technologies and where we're headed with them. The first one was called the Payload Orbital Delivery System, or PODS, which was developed for us by Space Systems Loral, MDA Brampton. So the idea behind PODS was, in order to get a higher tempo of small satellite access to GEO, why not take advantage of the 10 to 15 commercial satellites that are going there anyway every single year? So the way to make this simple was to attach all space-qualified equipment, but essentially just a pallet that is capable of ejecting a payload 70 to 100 kilograms into GEO. So the advantages are that it's modular hardware that's intended to be able to be easily integrated to any commercial satellite. So for fairly low cost, you can get a ride share. One of the reasons why it can be low cost is because you're ejecting, you can actually just do all the analysis with a mass simulator on the pod with the primary payload and don't have to slow it down at all. So you can just basically do that, qualify a range of mass, and then of course you're separating and doing your own thing. So it to a certain extent can help decouple some of the problems that we have with rideshare. Satlets is another entirely unique. This is a very difficult program to describe because it is so different from the way we build satellites today that it's very hard to explain. But think about a modular, scalable mini satellite bus. So a highly compact, about the size of a CubeSat, but having all the capabilities, or most of them, of a satellite bus. So I'm talking data management, cooling, propulsion, and even electrical power generation. So these satlets are designed to be snapped together so that you can build any size or shape bus. And the real magic is actually in the software. When you get these things close together, they form a mobile ad hoc network. So just like when you plug a new piece of equipment into your computer, it says, oh, I've got a new hard drive, or I've got a new mouse, or I've got another asset or a resource. So the software architecture is aimed so that you can easily add new pieces and take them out and develop a network and use each satellite as a resource. So one of the real powers of this is it's incredibly redundant. If one of these satellites has a problem with one thing that it does, another satellite can very easily take up the slack. So right now we're planning on demonstrating this in low Earth orbit. Next spring sometime we'll be launching on a Falcon 9 when they get back to flying. And the idea behind that is that we're going to demonstrate on the ground that you can rapidly integrate a payload. So you give the payload, and this thing snaps together in any orientation, especially with the constraints of rideshare. And then you can launch it into space. But the real benefits of this particular architecture, I think, will come when we have robotic capability in space. So think about the ability to repair a satellite by just swapping out a modular part. What about taking it apart and putting it back together in a different orientation with a new payload? So you can imagine almost immortal satellites at some point in the future. And finally, the robotic servicing element of Phoenix. So we have refocused this program, and we think the most important way of getting this capability is actually through a commercial partnership. We're very inspired by the COTS program and CRS and Commercial Crew. So together, we would like to do an invest together and support, and then eventually the government will be able to purchase servicing services back from a commercial operator. That is the program structure right now, heavily taking advantage of commercial industry. So what are the tasks? So we've looked at a lot of tasks, and we think these are the ones that are of most interest, at least to the current national security operators. So high-resolution images on request. When you send stuff to GEO, it's gone. It's all a mystery. If you have a problem, it's very difficult to see it. In diagnosing it with limited data, the number of times that we have figured out what was going on space station by just sending an astronaut to be able to go look at that, you're not able to do that in GEO. So we think that that is a very powerful, enduring mission that will go on and on. There are a lot of failures out there that we still don't understand. Cooperatively moving spacecraft in orbit. So obviously there's always going to be a trade-off, especially in a commercial business case, for how many maneuvers you're willing to do, because it'll reduce the lifetime of your servicer. But particularly think about specific examples like objects that could be pulled back to zero inclination in GEO. And then of course the ultimate case, which is expend all your propellant and get a ride up to the graveyard orbit. And finally, of course, the low frequency but high payoff cases where you've had a failure of a solar array to deploy properly, or an aperture where you can get in there with a robotic arm and mechanically assist that and recover the revenue. We think robotic servicing is actually absolutely critical to creating a vibrant, robust commercial ecosystem in GEO. And there are lots of different pieces to this, but robotics is absolutely essential. We've done this in LEO before, but GEO has a lot of different problems. First of all, the latency is much higher. Second of all, the radiation environment is much more extreme. So there are a lot of things left to prove technically that we would like to do. But once those things have been achieved, now you can start to see things like, if you have low-cost access to LEO, you can have solar electric tugs that go back and forth between LEO and GEO. You can see cases where you launch your payload empty without any fuel whatsoever and then get it serviced and refueled on orbit. And eventually, of course, the ability to create extremely large, modular, essentially immortal apertures and other platforms in GEO. And we think these are all the things that are enabled by servicing. Let me shift gears for a moment to space domain awareness. Orbit Outlook was a program that we started taking a look at the way JSPOC does conjunction analysis. They use a handful of very powerful, very capable sensor platforms, and those platforms are certified, and that information then goes into the conjunction assessment. Well, the problem with that is that to add more capability worldwide at higher tempo, you have to certify each of those data sources. So Orbit Outlook was a program that was aimed at bringing in commercial data sources. So think of university telescopes, commercial radars, commercial telescopes, and all kinds of sensors all around the world, and building the capability to absorb that information at the proper security levels, manage it, keep the bad data from polluting the good data, and being able to ingest much larger amounts of data, obviously at much lower cost. And our most recently started program in this area is called Hallmark. And Hallmark is aimed at real-time space domain awareness. So the idea is to create a test bed that we can draw in technologies that allow us to ingest all this additional data that we're going to get from Orbit Outlook and manage it and present it in a way that's obvious. And I can tell you that the four-dimensional information that is going on in space is not immediately obvious. It's not like any other system. So to try to visualize that information is very difficult to do. We'd like to take advantage of the most advanced displays in order to help the operators understand what is actually happening in space. And the impact for this program in particular, I think, is quite significant, because if we can transition to real time, we will then have the foundational basis for creating a space traffic management system, which I think as we get more and more commercial operators will be an enabling capability. I would like to wrap up here by saying that we think that all of these things are going to change the future. Robotic servicing is probably our next major thrust area. Of course, the XS1 program we're very excited about. I want to make a comment about the two programs on the bottom. One of the focuses, as I mentioned, of our technology is for national security. So wouldn't it be wonderful if someday our soldiers out in the field in very remote locations never had to worry? They could whip out a phone and they could get data and comms anywhere in the world, and it wouldn't matter. Did it come from a satellite passing overhead? Did it come from a UAV? Did it come from a traditional cell tower? It would be completely invisible to them, but it would be a secure network anywhere in the world at any time. So the ability to mesh all of these capabilities that are now completely separated from each other, we think is very important. And of course, the space element of that is going to be critical. In addition to that, we're very interested in advanced propulsion for space platforms and hypersonic platforms. We think that's incredibly important. It's enabling across all of our platforms. So we're currently considering investments in things like throttleable rocket solid rocket motors and new propellants that have better chemistry, more advanced chemistry that can provide greater ISP. So stay tuned, that's the picture for the future. Thank you.